The E8 Lie group is a continuous symmetry structure described by 248 dimensions. Since its discovery in the late 19th century, it has functioned as a pinnacle of mathematical complexity, existing entirely in the realm of theory. In 1989, Alexander Zemlyalikov proposed that this specific symmetry would emerge in the physical world during a quantum phase transition. Specifically, he predicted that E8 governs the excitations of a one-dimensional icing chain at its critical point. To test this, researchers used the quasi-one-dimensional ferromagnet cobalt niobate. In this material, cobalt ions are arranged in zigzag chains, where the primary magnetic interactions occur along the c-axis. By applying intense transverse magnetic fields, the team aimed to tune this crystal through its quantum critical point. They were hunting for a specific spectrum of 8 particles predicted by the E8 model. If the predicted particle ratios appear in the lab, it confirms that the most complex structures in pure mathematics dictate the behavior of matter at the quantum boundary. In its ground state at zero temperature, the internal forces of the cobalt niobate chain cause all magnetic spins to align in the same direction. This spontaneous alignment is known as ferromagnetic order, and it is driven by the Ising exchange, which favors spins pointing along a single axis. When a neutron hits the chain, it flips a section of spins. This creates 2 boundaries where the up orientation meets the down orientation. Physicists call these moving boundaries domain wall kinks. They are the fundamental quasiparticles of this one-dimensional system. In a perfect one-dimensional chain, these 2 kinks hop and propagate along the line independently of each other. This neutron scattering data shows the resulting energy distribution. Because the kinks move independently, they create this broad, fuzzy continuum rather than sharp, distinct particles. Without an external force to bind them, the excitations of a one-dimensional magnet are not discrete objects, but a continuous range of moving boundaries. In a real crystal like cobalt niobate, the chains are not isolated. Weak 3-dimensional couplings exist between adjacent chains. As the kinks on one chain move apart, they misalign with the neighboring chain, breaking interchain bonds. Every step further away increases broken bonds, creating a string tension, where energy cost grows linearly with distance. This mechanism is mathematically analogous to the strong nuclear force, which confines quarks within mesons so they cannot exist as free, isolated particles. Confinement changes the physics. The energy continuum of the free kinks is forced to split into a ladder of discrete, quantifiable bound states. We see this clearly in the low-temperature data. The previous blur has vanished, replaced by 5 sharp energy levels that represent the kinks trapped in their bound states. These sharp levels show that the surrounding 3-dimensional environment has imposed a strict hierarchy on the quantum particles. To reach the critical point, researchers apply a strong external magnetic field, perpendicular to the material's natural Ising axis. This transverse field stimulates quantum tunneling. Spins rapidly fluctuate up and down. As field strength increases, these fluctuations become increasingly intense. At the critical field of 5.5 Tesla, the fluctuations become strong enough to overpower the internal Ising exchange, melting the magnetic order. When the ferromagnetic domains vanish, the domain wall kinks lose the structure that allowed them to exist in the first place. In the resulting paramagnetic phase, the spectrum shifts to a single sharp mode, representing simple spin flips that cost Zeeman energy. At this critical threshold, the material's internal structural rules are stripped away, providing a clear window into the underlying quantum symmetries. The transition takes place in a narrow window of field strength, right at the edge of the critical point. Here, the theory states that the confined kinks must reorder into exactly 8 meson particles, with energies determined by the E8 Lie group. By analyzing the neutron data just below the 5.5 Tesla mark, researchers identified the first 2 resonances, M1 and M2. This chart tracks how the ratio between these 2 masses changes as the magnetic field increases. As the field nears the critical point, the mass ratio rises until it hits 1.618, the mathematical golden ratio, predicted for the first 2 particles of the E8 spectrum. The physical behavior of the melting magnet has aligned with the most complex continuous symmetry discovered in mathematics. These exact E8 ratios emerged despite the presence of interchain couplings and the imperfections of the crystal lattice. This is the power of universality. At a continuous phase transition, The microscopic details of the material are overridden by the macroscopic symmetry of the critical point. This experiment shows that by balancing kinetic energy against confinement potential, physicists can materialize exotic states that were previously thought to be inaccessible. At the quantum phase boundary, the material's chemical and structural properties yield to the symmetry laws of the transition itself. Mathematics provides the architecture that the quantum universe follows when its standard structural rules are removed.